I'm Karina Mauco. I'm a postdoc at the University of Valparaíso, and today I will talk about protoplanetary disks and how, using ALMA observations, we can characterize the dust content in a ring of dust, in this case, which is STRARS 91, which is a low mass star in a John stellar formation region. So this work is, of course, thanks to the collaborations of all these persons listed over here. So let's start. First, why do we care about protoplanetary disks? Well, protoplanetary disks are the natural byproducts of stellar formation. So once you have a collapsing core that will form the protostar, since you always have some degree of rotation, then you will naturally form the disk around the protostar. And the disk is going to be very important in the evolution of the system because it will set the final characteristics of the protostar and also of the planetary system. So if we want to understand how our solar system formed, we need to study the early stages of the system when the protostar is surrounded by these disks of gas and dust. So what is exactly a protoplanetary disk? Well, here I can show you a sketch, and you can see that, well, they are disks of gas and also dust, and they have very peculiar characteristics. First of all, they have this stratified distribution of dust. So you will have a smaller dust at the upper layers of the disk, at the surface of the disk, that will going to be sensitive to infrared scattered light, for example. But you also have these denser, colder parts of the disk, which is the midplane and very close to the star, where large grains reside. So in that sense, that will produce a very peculiar thing in protoplanetary disks, that different wavelengths, different frequencies will trace different regions. So if you want to be sensitive to the midplane, for example, you will need observations at millimeter or centimeter wavelength, like ALMA. And also you will see here on the sketch that the graded shaded regions, the gray shaded regions, shows the distribution of the gas. So you will see that will monotonically decrease with radial distance. So one very clear example of this is TW Hydra. You can see that if you observe it in a scattered light, so small grains at the upper layers of the disk, you can see one morphology. And if you go and observe it with ALMA observations, for example, you will see that the morphology is very different. So in order to study protoplanetary disks, you need multi-wavelength observations in order to have like the general picture of the system. And the gas normally is very extended in the protoplanetary disk. So you will have different processes happening at the same time. You will have dust settling, which is just the settling of the small dust to the midplane, where it will start growing. But also you will have the movement of the dust from the outer parts of the disk to the inner parts in the radial direction, what we call the radial drift. So one thing that we have noted over the years is that this radial movement of the dust is very effective. So basically the dust grains will move inward too fast, and the dust won't have time to stay in the denser regions and grow. But we know that planet Cis will observe it in a lot of different exoplanetary systems. So we need a process that stops the grains and be able to grow and accumulate in these systems. So in this sense, ALMA has been a revolution for this field. We now have these high resolution observations of these Jones systems with these around it. And you can see here, for example, in this very famous survey, the DCHART survey, this survey 20 protoplanetary disks at 1.2 millimeters, and you can see that all of them have these substructures. They have a ring of dust, they have bright rings, dark gaps. Also, you can see some spiral arms in some cases, and also some asymmetric emission. So we know that these substructures are now common in this system, these Jones systems. So one solution for this is that the distribution of the gas is not monotonically decreasing in the radial direction, but sometimes you can have these pressure bumps of these local maxima in the distribution of the gas. So those will go to that maxima and will get trapped there. And that's how you form these substructures and will promote, of course, grain growth. So now, if you want to study planetary system, then you need to look for sources with these substructures. So in that sense, STRARS 91, the source that we are going to be talking about here, is a very interesting source because it's what we call a transitional disk, which is a disk with a large cavity In this sense, you can see that from the ALMA observations, we know that is a ring of dust with a millimeter cavity around 86 AU. And from a scattered light, a scattered infrared light, you can see that small grains reside inside the millimeter cavity, as you can see here. For the gas distribution, the gas is well extended throughout the system, and that is pointing to dynamical querying by multiple planets, which is the most likely gut opening mechanisms in this source. So this source is a young star, 3 million years, is in the Lupus trimolecular cloud. It has had the mass of the sun and is actively accreting. And you can see here from the SED on the left that it has this classic morphology for a transitional disk. So we're going to study this source. What we did was observe this source with new high resolution ALMA observations at 2.1 millimeter. You can see here the continued image. You can see that we can clearly resolve the ring of dust with a huge cavity. And what we want to do is use this data set with a previous archive data at 0.9 millimeters and 1.3 millimeters to estimate the spectral index, which is the slope of the SED in the ALMA observations, which is going to give us some clues about grain growth, and also make a radial analysis of these ALMA SED, including a model that includes scattering effects and also optical depth effects, to be able to estimate simultaneously the optical depth, the dust surface density, and also the maximum grain size in this ring of dust. So here I show you some results. These are the radial intensity profiles for the 3 data sets that we use. You can see that all of them peaks around 90 AU, where the dust ring is located. And with this data set, we estimated the spectral index. So you can see here on the right is almost constant throughout the ring of dust. Here is from 60 to 120 AU, where the ring is supposed to be. So you can see that the spectral index has an average value around 3.34. So in order to estimate the maximum grain size, we use 2 different approaches. One is the classical approach, where you assume that the emission is optically thin and you neglect scattering effects. And in that case, you can estimate the spectral index here with this equation here, where beta is just the absorption coefficient. And if you take that into account, then the maximum grain size is around 1 millimeter to 2.5 millimeters. But we wanted to do a more realistic approach, including optical depth and also scattering effects. So for that, the first thing that we estimated with our model is the optical depth. So in this case, I show you here the optical depth as a function of radius. Again, this is only valid over here where the ring of dust is located. And you can see that for the pure absorption case, without including scattering, which is the dashed lines here, we found a peak optical depth from 0.1 to 0.01. But in the more general case with scattering, we found peak optical depth values very similar to the ones found in the B-chart sample, the one that I showed you before. So we can safely say that the dust is not optically thick, so we can use this data set to estimate properly the characteristic of the dust in this ring. So now for the dust mass and for the maximum grain size, I can show you here the dust surface density that we found when we include this optical depth and scattering effects, which is here on the left. And by integrating this predicted surface density, we can have an estimation of the dust of solids in the system. What we found is that it's 31 air masses, more or less. And on the right, you can see the profile, the best profile for the maximum grain size. And you can see that it's also almost constant throughout the ring of dust. And has a value of around 0.6 millimeter. So we can safely say that there is accumulation of dust there. There is dust growth because these grains have a maximum grain size of at least 0.6 millimeter. So one thing that we want to highlight is that if you use the classical approach of assuming the emission to be optically thin, then you can easily overestimate the maximum grain size, as you can see here, and also underestimate the mass of solids in the disk. And that can be a solution for the mass bucket problem for planet formation, where dust mass in protoplanetarities appears to be too low to explain the observed exoplanetary system. So in that case, the problem here is that we are using the wrong assumption, and more evidence and papers are pointing to that this optically thin emission as a millimeter wavelength is probably wrong. So that's something that you have to take into account when you study protoplanetary disks. Now, putting TRAS-91 in context in the spectral index, we compare the spectral index that we found with the rest of the population, this population in lupus. And you can see here the spectral index at these wavelengths as a function of the flux at 1 millimeter. And the spectral index has been widely used to estimate the maximum grain size because it's a proxy for maximum grain size, as you can see here. So lower spectral index implies larger grains. But you have to be careful because, as pointed out by Su 2019, optically thick emission also produce the same outcome. So one possible explanation for this difference between TRAS-91 and the rest population of lupus is that the lupus population is mostly composed of small compact disks. So these disks are probably optically thick at this wavelength, and that is why it's lowering the spectral index. And that's why TRAS-91 stands out as the source with the highest spectral index, because it has this huge cavity and this ring of dust at about 90 astronomical units. And that is very in line with what we found when we compare TRAS-91 with other transitional disks in other regions. So here I show you the spectral index as a function of cavity size for the sample of transitional disks found in Pinilla 2014. And you can see that they found this relationship of the spectral index and the cavity size in transitional disks. And you can see that TRAS-91 perfectly fits these relationships. So this source expects behave as expected for a transitional disk with a huge cavity. And they explain this relationship because the emission here is being dominated by the dust at the rim of dust at the cavity. And if you have wider cavities, then the maximum grain size will be lower, and those particles will feel less radial drift, and then turbulent motions will be the main source of the structure collisions. And in that case, the maximum grain size will also scale with the gas surface density, which decrease with radial distance. So you can see here that TRAS-91 perfectly fits this relationship. So, and that is also in line with what we found here, where most probably the difference between the spectral index here is because these sources are mostly very small disks and probably optically thick. Yeah, so now we use these observational results and try to interpret them using a model that includes dust growth, fragmentation, and also planetesimal formation. In this case, is this model from Stamler 2019, and they use this model to explain the second ring, the emission from the second ring of this source, which is a HD 163296, which is a B-chart observations or target. And you can see here that they use this surface density where they have a gap, a cavity at 83 AU, and you have the ring of dust located at about 90 AU or 100 AU. So it's very similar to what we found in TRAS-91. So we compare this model with our observations. They use this model and evolve it with time using all these processes to explain the peak optical depth found in this ring. And what they found is that when you start evolving the model with time, you need planetesimal formation, as you can see here. This is the peak optical depth as a function of time, and you need planetesimal formation in order to remove millimeter particles from the midplane in order to decrease the optical depth and feed it into the observed values. And also, most important, if you see the spectral index here, so here's the millimeter spectral index as a function of distance from the star. Once you start evolving the model with time, in time, the spectral index will reach a minimum value and will be almost flat, and will range between values between 3 and 3.5 when you include planetesimal formation. So comparing this work, this model with those growth of fragmentation and planetesimal formation, we see that we have these similarities. We found the similar peak optical depth. We have that spectral index is almost flat throughout the ring, and that can, one solution for this is that one likely scenario for explain these observational features is that planetesimal formation is ongoing in this ring of dust, and that has been also reported as an extremely robust process in protoplanetary disks. So here I leave you with my conclusions of using ALMA observations to characterize the dust content in a transitional disk, and we found that evidence of grain growth and also possible planetesimal formation in this ring. So if you have any questions, I'll be happy to answer any of them. Thank you.
Thank you very much. It's a great talk, very interesting stuff, definitely. I I think I do not see any questions yet. So let's give the people a moment. So maybe I'll ask something. I think I might have missed it, but you said before your observations showed that the dust was optically thin, but still the assumption of optically thin emission was not correct.
Yes.
Could you?
Well, yes, the emission is at least marginally optically thick. I mean, if you see here, even in the more general case, when using scattering effects, you found an peak optical depth of less than 1. So at least it's marginally optically thick. But what is interesting is that even in this case, when the emission seems to not be optically thick, but just a little bit, when you estimate the mass using the classical approach, assuming that the emission is optically thin, then you will underestimate the mass at least by a factor of 2 or 3. So that just tells you that you have to be very careful when you assume that the emission is totally optically thin, when estimating the mass, because you will underestimate the dust mass in the system. So that is why it's very important to include all these effects, optical depth and also scattering effects, which will lower the emission of the system in order to estimate or characterize properly the characteristic of the source.
Great, thank you. Are there more questions?
There is one question. In addition to the formation of planetesimals or planets, are there any other possible explanation for the presence of these rings? And if so, how could we distinguish if it is due to planets or something else?
Yeah, one very, very, very good question. Of course, there has been proposed different processes that doesn't include planets to explain these substructures, because if you see, the main age of these systems is 1 million years. So they are very young systems. So if planets are really responsible of these substructures, then planets have to form very, very, very fast. So this alternative approaches without planets that have been proposed has been a gravitational instability. So you have like a concentration of dust, and then it will collapse and will form planets. Other processes has been these zonal floats, which includes the behavior of the magnetic fields, which if you have a certain configuration of the magnetic fields, for example, concentric annuli of the magnetic fields, then these can also trap dust and can produce these substructures. But that is actually an open question right now in this field, and that's why high resolution observations with ALMA, not only of the dust, but also in molecules in the gas, which also has been made right now, is going to be a key in order to disentangle between these two possibilities, that if these substructures are actually the results of planets, or these are the precursors of planets. So that is an open question. It's a very interesting field, and I think ALMA is going to be crucial in order to answer which of the two is responsible for these substructures.
Great, I think we have time for one more question.
Yeah, there is one more question. Is there some material lost away in the disk evolution, or is all the material to be accreted into the star and planets?
Yeah, there's a lot of different mass loss processes in these young sources. I always said that just as humans, when they are very young, they are very rebel, so they are crazy and they are all chaotic. So when these sources are very young, as these ones that I show you here, they have these stellar winds, they have bipolar jets sometimes because of the accretion process. So these are all mass loss mechanisms that will, of course, be significant in the evolution of the system. So you will lose a significant fraction of the gas and the small dust, which is coupled to the gas, in these first early stages of the system. So yes, there are a lot of mechanisms that can produce mass loss in these systems.
Great, thank you very much.